All right, so welcome to Math 389 Advanced Analysis. This is lecture 23, and we're going to be talking about heuristic calculations today. And so it was really good that I was asked about a probability question. The specific probability question I could have done without, but because what I want to do today is I want to use one of my favorite techniques from probability, linearity of expectation. So out of curiosity, how many of you have seen linearity of expectation? Has everybody seen this? Okay, so we'll then do it somewhat quickly. That doesn't want to advance. Okay, and so we're going to, wow. So we're going to do it in 4 settings, maybe, or 3 settings. We're going to look at Fermat primes, random primes in the Riemann hypothesis, twin primes, maybe triple primes, and just talk a little bit about how might you predict answers to questions related to this. How might you figure out how many twin primes are there up to x? Are there infinitely many as x gets larger and larger and larger? Are there infinitely many Fermat primes? How would you come up with a heuristic for something like this? And so the big idea is the linearity of expectation. So the expected value of a sum is the sum of the expected values. Now, if I looked at the variance of a sum, is the variance of the sum of the variances? When are they the same? Independent. So it's the sum of the variances if independent. If they're not independent, is it possible that the variance of the sum could be the sum of the variances? Yeah, you could just have all the covariance terms, cancel each other out. So it's not an if and only if. But if they're independent, then the variance of the sum is the sum of the variances. If you don't have independence, you can often estimate how bad the variance can be by using Cauchy-Schwarz or stuff like that. And so for some problems, we don't really care about the actual value of the variance. We just care maybe how does it depend on n or something like that, or some parameter. So for a lot of things, it's fine. The expected value of a sum is the sum of the expected values. What's great is this is true irregardless of whether or not the x's are independent. That's what makes it so useful and so applicable, is we do not need independence. So no assumption of independence here. And the proof is basically you would integrate x1 plus xn times the joint density function x1 through xn, x1 dot 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 xn, dx1 dot 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 dxn. And now the integral of a sum is the sum of the integrals. And so this will look like a sum I equals 1 to n. You would have the integral, let's say xi f x1 dot 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 xn x1 xn dx1 dxn. And then for each of these, if I fix xi and integrate everything else, I'm left with the density of just the real variable xi. So this is going from a joint density function to a density function. I'm basically saying, I don't care what anything else takes on. So probably a Zoom issue. All right, having trouble getting in the Zoom? Okay. Yep, okay. You should be in now.
Yes.
Okay, yep, you're welcome. Okay. So we're just doing linearity of expectation right now. Okay, and so we then get that this is just then going to be a sum I goes from 1 to n of the integral of xi, and now just the density function of xi. And each one of those is then just going to be the expected value of xi. So we don't need independence. What independence gives us is the joint density function factors as a product of the density functions, which would then make the variance calculation, much, much nicer. But for the expected value of a sum, we don't need that. All right, so now what we're going to do is we're going to look at special primes. So in particular, Fermat primes. How many of you have seen Fermat primes before? Okay, so one person a little bit. So can a number of the form 2 be prime?
What do you mean of the form
2. Yes, right. So that's fine. What if I give you the number 2 to the m? Could that be prime?
Well, depends on the power.
Yeah, depends on the power. So if m equals 1, it can be prime, but only for m equals 1 can it be prime. So if I try to find primes in the sequence 2 to the m, because everyone but the first is, I'm sorry, because they're all even, only the first one can be prime. So let's look at numbers of the form 2 to the m plus 1. Those at least have a chance to be prime. And we can start looking at values of m and what we get. So when m equals 0, we would get 1 plus 1 is 2, which is prime. When m equals 1, we get 3, which is prime. So it turns out that this sequence is always prime no matter what m is. Yeah. I checked it for 2 cases, right? Should I check it for one more case? 2.
Not in order.
All right, let's check 2. So we get 4 plus 1 is 5, okay? Is that enough data? No, it actually turns out 2m plus 1 is the mth Fibonacci number. 2, 3, 5, 9. So again, small data, you should not be making conjectures based on this. Should I be doing this by hand? No, I should be writing a computer program and just spitting out a huge number of them. All right, if I do 3, I get 8 plus 1 is 9, so that's not composite. Right? If I do 4, I get 17, which is prime. What about 5? 33, which is not prime. If I do 6, 65. If I do 7, it would be 129. So it's always composite from this point onward. Well, let's do one more. 8, we get 257. Is 257 prime or not? What's the largest number I need to check to see if 257 is prime?
I think it is prime.
It is prime. It's not divisible, I think. The sum of the digits is 14. So if a number is composite, I can write a composite number as, say, x times y without loss of generality. At least 1 is at most square root of n. Because if they were both less than square root of n, I'm sorry, if they were both greater than square root of n, then the product is too large. If they're both smaller than square root of n, the product is too small. So at least one of them is at most square root of n. So I only have to check up to the square root of 257. Well, let's see, 257 is 2 to the 8th plus 1, right? So the square root is really, 17 is too large. 17 times 17 is going to exceed this. So I just have to check all the primes up to 16. It's not too bad to see it's not divisible by 2, by 3, by 5, by 7, by 11, 13. Okay, I do a little quick division. Okay. So do you think that there are more primes in the sequence 2m plus 1? And which m do you think work?
So far it's the powers of 2.
Yeah, so far it's the powers of 2. So it's, 0 works, 1 works, 2 works, 3 doesn't, 4 does, 8 does.
Are you considering 0 to be a power of 2?
I am considering right now 0 to be a power of 2. But if you want, you can put that in gold, which is fine. So maybe conjecture, if 2 to the m plus 1 is prime, then m is of the form 2 to the k for some integer k, except for m equals 0. Unless you would allow me to put in like k equals negative infinity, but no. So again, one of the things I want to talk about in this class is how do you do mathematics? How do you do research mathematics? We gather data. I should not be doing this by hand. I should be doing large amounts, but this is fine. I know the pattern kicks in pretty quickly. So do you think that this pattern holds, that it's only the powers of 2?
Check for 16.
So you could check 16. So if we do 16, that's 2 to the 16 plus 1. And so how do we do something like that? Do we multiply this out by hand?
40,000.
Oh, there's like 37,000. I'm trying to go to Wolfram Alpha right now, but it's not loading on my phone. If somebody can load it like Wolfram Alpha.
No, wrong. It's 65,000.
Oh, 65. Okay. So it's, what is it, 65,000?
537.
Oh, sorry, the 37 is at the end, not at the start. And that is prime. So this is making you feel, a little bit more confident that maybe the powers of 2 are prime. But you've got to be very careful whenever you do anything that you make the right conjecture. So I'm a huge fan of Mark Twain's witticisms. One of them is, a cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one. To each experience in life, only draw from it what you should. Be careful of drawing too much. What we're seeing here so far is that powers of 2 are leading to primes. Non-powers of 2 are leading to composites. Maybe if m is not a power of 2, it's going to be composite. And maybe if m is a power of 2, it has a chance of being a prime, but is not always a prime. Does that seem reasonable? So here you get, these are weak conjectures. So conjecture 1. If m is not a power of 2, 2 to the m plus 1 is composite. And then conjecture 2, if m equals 2 to the k, then 2 to the m plus 1 is 2 to the k plus 1 is prime. One of these is known, one of these is open. Any thought on which one you think might be open? Or which one you think might be known?
I'm guessing the composite is known.
The composite is known. And so the question is, can we come up with a factorization? So let's consider, more generally, let's say x to the ab plus 1. And so we are assuming m equals ab is not a power of 2. So what can you tell me about a and b? So what would be a good way to write m? If it's not a power of 2, how should I write m?
Power of 2 times something.
Yeah, so let's let a equal 2 to the k and b equal an odd number. right? Any integer m has a decomposition like this, and we know b is an odd number greater than 1. Now, it's possible that k equals 0, in which case m is just that odd number b. But if I'm assuming m is not a power of 2, then let me explicitly convert that to math. What does it mean not to be a power of 2? It's some power of 2 times some odd number that's greater than 1. So we have x to the a to the b plus 1. Let's call that y to the b plus 1, with y is x to the a, which is really 2 to the a. Can you give me a root to the equation y to the b plus 1 equals 0? Can we factor that? Remember, b is an odd number. So what value can I put in for y and make this equal 0? -1. This is why I wanted to write it as x to the ab y, because if I'm writing it with 2, I can't just say, let's let 2 to the a equal -1. But this has to factor. Y to the b plus 1 equals 0 has y equals -1 as a root, since b is odd. So y to the b plus 1 factors as y minus 1 times
y to b minus 1 plus y to b minus 2.
Yep.
plus y minus 1.
Since you have two terms at the very front, you should really have two terms on the far right, and balance the two, right? You don't. Okay. We'll just go down to 1. We can play favorites. Okay. So this is a nice factorization. How can you check and see if this is right? Just multiply it out, right? So it was inspired that you saw this was the factorization. There's a lot of things where it's much easier to check than to come up with. Now that we know that this is a proposed factorization, if we expand, we can see that when we multiply, the minus sign is going to have all the stuff come in with an opposite sign as the y. They're going to be shifted by 1. It's going to be a telescoping sum. The first term, y times y to the b minus 1 survives, and then all the stuff in the middle cancels, and then the -1 times 1 survives at the end and gives us the, oh, wait a minute. Is this what we want? Because if we multiply, no, it's y plus 1. Wait a minute. It's y plus 1 is the root.
Oh, yeah.
And so what's the factorization now? Do we agree that there has to be some factorization? How can we find what the factorization is? So it could be alternating. What should we do? How should we find it?
Well, it's not, if you know -1 is a root, you know the y plus 1 term has to be there, you could just do long division.
You could do polynomial long division. But right now we're trying to do it for general odd number b. Instead of trying to do it for general odd number b, what should we do? Yeah, let's do some specific. Let's gather data, right? So when in doubt, always gather data. So when b equals 3, we get y cubed plus 1. That's going to be y plus 1. And then it's y squared. We have to have a plus 1 at the end. So it's going to be y squared minus y plus 1. And when we look at what happens, this is going to give us, this would give us a y cubed, a negative y squared, and a positive y, right? And then over here, this is going to give us a y squared, a negative y, and a plus 1. So we can see all the intermediate stuff cancels. If we try b equals 5, we can try to do the polynomial long division. We have y plus 1. And now this proposal of doing this alternating, this would be y to the 4th minus y cubed plus y squared minus y plus 1. Yeah, this makes sense. For instance, when y hits the y cubed, that's going to give us a plus y to the 4th. And when the 1 hits the y, so that's going to give us a minus y to the 4th, that's going to give us a plus y to the 4th, and they're going to cancel. And so that's going to be the factorization. And when you look at this, every time we increase the exponent by 2, we add one more positive, one more negative term. Everything is going to be fine. So we have x to the ab plus 1 is y to the b plus 1 is y plus 1, y to the b minus 1 minus y to the b minus 2 plus y to the b minus 3 minus dot 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 plus 1. But x is equal to 2, right? So we get 2 to the m plus 1 is, oh, wait, this is not green. This is not correct. Did I make a mistake? Can somebody just quickly look up for my numbers? Is it with a plus 1 or a minus 1? I'm not. I don't seem to be getting web service in here right now. It's plus 1. And so sorry. Oh no. Okay, this is fine. Okay. This is fine. I had forgotten what we were trying to prove. So we get 2 plus 1, and then we'll get a, I'm sorry, 2 to the a plus 1, right? And then we'll get 2 to the a to the b minus 1 minus 2 to the a to the b minus 2 plus dot 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 plus 1. Is this number prime or composite? Composite, right? This is clearly at least 3. Oh, sorry, at least 2. If a equals a could be 1. No, right. Because we could have no even powers, right? M is equal to AB. It's 2 to the k times an odd number. So we could have k equals 0. If k equals 0, then 2 to the a is going to just be 1. But we'd have 1 plus 1 is 2. So if a equals 1, this is k equals 0, we get 2, else it's at least 3. So this first number is not going to be 1. So all we need to know is this number over here is greater than 1. Is it clear that this number is greater than 1? Yeah, why? So you have 1 at the end, and then if you look, you always have the positive number followed by a number that's smaller, right? So positive number followed by smaller negative number. So that is positive. Add 1, so at least 2. So it has to be composite. And that's the proof. Now, I was getting confused for a second, but I wasn't trying to show that the factor was 1. I was trying to show the factor was greater than 1. And so the 2 to the a plus 1 is exactly what we wanted. So we've proven the first conjecture, that if you're of the form, 2 to the m plus 1, if m is composite, we have a trivial factorization, so you can't be prime. So the only possibility is if m is a power of 2. Okay, so if m is a power of 2, there's a chance. Okay, so now we call these Fermat primes, or Fermat numbers. Named after, come on, this is a marshmallow question. Who do you think Fermat numbers are named after? Yes. Your Fn is 2 to the 2 to the n plus 1. And so when n equals 0, you get 2 to the 0 is 1, so you get 2 plus 1 is 3, which is prime. When n equals 1, you get 4 plus 1 is 5, which is prime. When n equals 2, we got 17, which is prime. When n equals 3, we got 257, which is prime. When n equals 4, we got the 65,000, was it 537? Okay. Which is prime. Conjecture. No other n gives a prime. So it's just these numbers. There's a lot of stuff you can do with these numbers. You can actually use these, I believe, to prove that there are infinitely many primes by showing that I think the Fermat numbers are pairwise relatively prime. And since they're pairwise relatively prime, you've got to be generating new prime numbers as you look at new Fermat numbers. So I'll leave that as an exercise for you to see. Are the Fermat numbers relatively prime? How can we figure out how many numbers in the Fermat sequence should be prime? So we're not going to do anything rigorously today. We're going to try to do heuristics. So one of the key ingredients is the prime number theorem. How many of you have not seen the prime number theorem? Okay. This I could kick you out. No, I can't kick you out for this. So this is a beautiful result. If pi of x is the number of primes less than or equal to x, then the prime number theorem says pi of x is approximately x over log x. Okay, so the number of primes up to x is about x over log x. So in particular, the spacing between primes of size x is approximately, I have an interval of size x, I divide by the number of items I have, and that's going to be of size log x, approximately. So if you're at height x, you have to wait about log x until you see the next prime. Another way of looking at it is a number of around x, the probability it's prime is about 1 over log x. So the probability x is prime is approximately 1 over log x. Of course, this is bullshit, right? For a given number, it's either prime or it's not. It's completely deterministic. So what we can do is we can construct a random a sequence of random primes. Declare n prime with probability 1 over log of n. So the probability n is a prime in quotes is 1 over log n. We can let xn be the binary indicator variable, as to whether or not we've declared n to be prime. And then this will be 1 with probability 1 over log n, and 0 with probability 1 minus 1 over log n. And so now we can ask, what's the probability that a given number is prime? To first order, I'm going to just say it's 1 over the log of that number. This will give me the right density. Let's apply this to the Fermat numbers. So let's let yn equal x1. Well, let's do x f1 plus dot 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 plus x fn. So this counts the number of Fermat primes with index at most big N. And so now, what is the expected value of y and how many do we expect to have? Give me a formula for it. What's the expected number of Fermat primes with index at most big N? Yeah. And so this is interchanging order of operations. The expected value of a sum is the sum of the expected values. And I'm being very careful. I'm only going up to a finite index, so I don't have to worry about infinities. I can justify. So this is just going to be the sum, n goes from 1 to big N, of the expected value of x fn. But each one of these, so the sum n goes from 1 to big N, is 1 over the log of fn. All right, so this is the sum, n goes from 1 to big N, 1 over the log of 2 to the 2 to the n plus 1. Will you allow me to drop the plus 1? Does that make things larger or smaller? If I drop the plus 1, it makes it larger. I've made the denominator smaller, so this is going to give me an upper bound. Oh, good. I like upper bounds. A lower bound is going to be useless. If you're trying to show are there infinitely many numbers, I've shown there's at least 3. Okay, that's not going to help me as to whether or not there's infinitely many. If you show me that there's at most 18, then I know it's not infinite. So this is going to be less than or equal to the sum, n goes from 1 to big N, of 1 over the log of 2 to the 2n. What's the log of 2 to the 2n? This is just the sum, n goes from 1 to big N, 1 over the log of 2, 1 over 2 to the n. Right? But I can set that sum up to infinity, and that's still going to be up above. So it's less than or equal to 1 over log of 2, the sum, and it goes from 1 to infinity of 1 over 2 to the n. What is the sum from 1 to infinity of 1 over 2 to the n? It's 1. So this is just 1 over the log of 2. Does anybody know what the log of 2 is, base E? It's like 0.69. Yeah, I think it's about 0.69. So it's about 0.7 or 7/10, 10/7, around like 1.3. So this whole thing here should be less than 2. So if we've done things properly, we've shown that there should be at most 2 Fermat primes. Because we expect there to be 2 Fermat primes. So how do you feel about that answer? Right? So, you get to fill out evaluations. Have I wasted your time? I mean, is this a bad result or is this a good result? Did I do a good job or not? I'm getting a finite number for the number of Fermat primes. Yeah, I'm off by a little bit. And again, we're saying that the prime number theorem is the number of primes up to x is about x over log x. This becomes much better the larger x is. For small values, it's not so good. And so the fact that it's giving me a nice finite number, I think that's perfectly valid. I think this is actually quite reasonable. It's telling us I do not expect there to be many from our primes, that it's hard to be a prime, and there's just not enough of these numbers. They're more than exponentially apart. The exponent is exponentially growing. That's how bad this is. Right? These numbers are shooting off to infinity very rapidly. So for them to hit the primes in the sequence is going to be really hard. So this is the power of these methods. Let's apply this to another problem now. And so let's apply this to twin primes. So I want P and P plus 2 to both be prime. So let's do a heuristic. So as before, let's say xn is 1 with probability 1 over log n, and 0 with probability 1 minus 1 over log n. So this is basically declaring n to be a random prime. Okay, let's let Tn be 1 if n and n plus 2 are both random primes, and 0 otherwise. And then let's look at T1 plus T2 all the way up to Tn. That will count the number of twin primes up to basically n.
And it has to be larger than a certain value, right?
What do you mean?
Because if you have probability 1 over log n, then log n has to be greater than 1.
Right, so for instance, if n equals 2, we would have an issue. So n should be at least 3, yes. So I am quite happy to fix this, and let's start counting at 3. Good. So what do you think? So the expected value of the sum is going to be the sum of the expected values. What do you think the probability of n and n plus 2 both being random primes is? I'm sorry? It makes life easier, right? So let's assume independence. Right, then we would get the expected value of Tn is equal to the expected value of xn plus 2, which would be the expected value of xn, expected value of xn plus 2. So we would then get that this would be the sum, and goes from 3 to big N, of 1 over log of n plus 2. And what is that sum approximately equal to? Yeah, it's basically 1 over log squared of n. What do you think? Converges or diverges?
Diverge.
Diverges. Why?
Well, because it's greater than 1 over, like the series 1 over n, I think.
Yeah, good. So we know it's greater than 1 over n, so we expect a divergence. And then the question is, how rapidly does it diverge? And so I'm not sure if any of you have seen these asymptotic games. This is one of the reasons why I wanted to talk about this. This is an advanced analysis course. I want to show you some techniques. How can I get a feel for this sum? So we have a sum, n goes from 3 to n of 1 over log squared of n. And again, if you didn't like the dropping off the n plus 2 as an n, bump up the n to n plus 2, and then just drop the first term. So it's really not a big deal. So let's draw the real line not to scale. Here's n. Here's maybe n to the 1 minus epsilon. Here's maybe n to the 1/2. Here's 100. Here's 1. When I look at log squared of little n, and I'll even put maybe like a log n over here. When I look at log squared of n, how big is that? How much does it change? So we want to analyze log squared of n. If n is less than or equal to n to the 1/2, what would we get? We would get log squared of n would be less than equal to log squared of n to the 1/2. So that's going to be of size 1/4 log squared of n. Okay, well, you know what? That's actually not that far off from the log of big N. It's differing only by a constant factor of n to the 1/4. How much of the interval is covered from n to the 1/2 to n in the limit? What fraction of our numbers are at least n to the 1/2? Most of them, almost all of them, right? If you look at the fraction of numbers that are at most n to the 1/2, it's n to the 1/2 over n. That goes to 0. Almost no numbers are smaller than n to the 1/2. What about n to the 1 minus epsilon? What fraction of the numbers are at least n to the 1 minus epsilon? Not infinite. Also, almost, no, not 0. What fraction of the numbers are at least, wait, how did I phrase it? This is like one of those helplines. In order to better serve you, we are recording this call, so we could actually go back and check and see what did I say. What fraction of the numbers are at most n to the 1 minus epsilon in the limit? What fraction? So what fraction of the numbers are at most n to the 1 minus epsilon of the numbers up to n?
N to the 1 minus epsilon over n.
Right, which is just 1 over n to the epsilon, which goes to 0. Almost no numbers percentage-wise are smaller than n to the 1 minus epsilon. Almost every number is at least n to the 1 minus epsilon. So when you look at your values of n, I can split my sum as the sum n goes from 3 to, let's say, n to the 1 minus epsilon, 1 over log squared of n, plus the sum n goes from n to the 1 minus epsilon, I don't care that, to n of 1 over log squared of n.
If you're taking n to approach infinity, then doesn't n to the epsilon eventually get so long?
Right, but what I'm looking at is what fraction of the numbers up to n do I expect to be twin prime pairs? So I'm trying to get the big N dependence. So over here, for the terms here, I make things largest by replacing all the logs with the log of 3. Right? And the number of terms is n to the 1 minus epsilon. So this is at most n to the 1 minus epsilon over the log squared of 3. What about this? This, well, if I make everything smaller, I make it larger. If I make everything larger, I make it smaller. So this is going to be, at least the sum n goes from n to the 1 minus epsilon to n of 1 over log squared of n. And at most, the sum n goes from n to the 1 minus epsilon to n of 1 over log squared of n to the 1 minus epsilon. It's sandwiched in between those. And so we know that this sum is going to be, we get a 1 minus epsilon squared. So we get a 1 over 1 minus epsilon squared. N over log squared of n is less than equal to our sum, and goes from n to the 1 minus epsilon to n of 1 over log squared of n is less than equal to n over log squared of n. So what this tells us is if we look at this counting, if we assume independence, then the expected count is on the order of n over log squared n. And it looks like the correct constant might be 1, because I can make epsilon as close to 0 as I want. And because epsilon is a small positive number, this is a lower order term. This is n divided by n to the epsilon. The other one is n divided by log squared. Log squared is a lot smaller than n to the epsilon for any fixed epsilon. So this is a really good way to handle problems like this, is you break up the interval and say, look, almost all of the interval I just don't care about. I can bound it trivially. And the reason is the log function is so slowly varying that if I go all the way down to n to the 1 minus epsilon, it doesn't matter. If you want to, you could try to play fancy games. I'm not going to go down to n to the 1 minus epsilon. I'm going to go down to n over, say, square root of log n, or maybe log n to the 5th, something like that. There's no need to play fancy games like that. This is more than enough. And this shows us that we expect the number of twin primes up to n to be growing with n. We expect it to be on the order of n over log squared. Very different than the Fermat numbers. Do you like this result?
Assuming that the twin primes are independent.
Assuming that they're independent. And it kind of makes sense, if they're independent, the probability that your prime is 1 over log n, and the number of primes is n over log n. If I have now both of them, that gives me an extra log n in the denominator. Seems reasonable. Should we investigate further to see if this is reasonable, or just be happy? This is a loaded question. As good scientists, your answer is forced on you. Should we do further checks to see if this is reasonable, or should we say, it worked in this case, it should be fine? What's the answer?
Look further.
Look further, right? Always look further. Einstein has a great quote, it doesn't matter how many experiments, support my theory, if even one disproves it, my theory is worthless. So instead of looking at twin primes, let's look at prime triples. So prime triples. So we want n plus 2, n plus 4 to be prime. So we'll let maybe fancy T, that's the italics T. Is that right? Yes? People aren't sure. All right, we'll do math fraction. Tn will be now math cal T1 plus ... plus. I'm sorry? Oh, yes, you're right. In the future, it would actually convert this to tech, probably in about 10 years. We're not there yet.
We are there.
But it'll convert to tech in real time, as I write.
Someone,
I'm probably
one
can.
of my friends sent me a script that does image recognition, like text to text.
Okay, I actually am not surprised. When I was in France last year, I took a picture of the menu, and it was able to convert the photo of the menu and give me an English translation of the menu. So, all right. So what do we want to assume here? We'll assume independence. Assume independence. So math cal of tk, if we want to take the expected value of that, that would be the expected value of xk, xk plus 2, xk plus 4. So that would be the expected value of xk, expected value xk plus 2, expected value of xk plus 4. And that's 1 over log of k, 1 over log of k plus 2, 1 over log of k plus 4. And what does this approximately equal? Log cubed. So similar argument gives there exists constants alpha and beta greater than 0, such that alpha n over log cubed of n is less than or equal to the expected value. Did I make a mistake? Okay, mathfrak t n less than or equal to beta n over log cubed of n. So do you agree that a very similar argument, because we just have an extra factor of log, so just put an extra factor of log in all the calculations, the 1 over epsilon squared becomes a 1 over epsilon cubed. So the number of prime triples should be of size n over log cubed n. Do you like this result? Why not?
Because I only know one example.
Well, that's just because you haven't looked hard enough. I mean, what example do you know? So we know 3, 5, 7. Does anybody else know any other examples of prime triples where each is 2 more than the previous? There are no others.
No.
Yes. We can prove it in less than a minute.
One of them always has to be a multiple of 5.
Nope, but you're close. One of them has to be a multiple of 3. So if I give you, let's assume n is greater than 3. So n is either 1 or 2 mod 3 if n is prime. So if n is congruent to 1 mod 3, then n plus 2 is a multiple of 3. If n is congruent to 2 mod 3, then n plus 4 is a multiple of 3. So the previous heuristic fails. I wanted to write something stronger, but I'm not sure how good YouTube's profanity detector is and would it detect text versus audio. What went wrong? We can't just multiply them. So we were assuming that they were independent. They're clearly not independent. If I know a number is prime, what do I know about the numbers near it? Do you think they're more or less likely to be prime?
At least one of them is less than no prime. This has to be.
It's less likely, right?
It's a little bit less likely because for my number to be prime, it can't have a remainder of 0 when you divide by any prime less than it. So when I move a little bit, I have a chance of moving to a remainder of 0 by one of those primes. So if a number is prime, it has a little bit less chance of being prime next for its neighbors. And if you have sufficiently many neighbors, at least one of them is going to be a multiple. So this heuristic needs to be fixed. So we need to somehow take into account if a number is prime, that the probability that the next number is also prime has changed.
Next odd number.
The next odd number. So if we were to use random primes, then this would be fine. This is a property that random primes have that primes do not. So for a lot of difficult problems, we try to model complicated systems, complicated deterministic systems with nice random systems. And with these nice random systems, we can often make wonderful predictions. In this case, the prediction does not match with the primes. And so this model of randomly determining a prime to be a number to be prime with probability 1 over log n, this is called the Kramer model. It's a very simple model, but this calculation shows that it does give different predictions in some cases than the actual primes have. In other things, it does a great job. And again, the constants may be off by a little bit. Okay, it's a little bit of arithmetic, that's fine. We can try to fix things, right? Isn't it good to try to fix things? So if n is prime, what is the probability n plus 2 is prime? I don't like to subtract. Subtracting is very bad. What do I like to do instead? Nope. Okay, I will accept divide because I was thinking of multiply. But dividing and multiplication are very similar. So I will accept divide. So we need to rescale the probabilities. Rescale the probabilities. So imagine we have some number here, n, and it's prime. It's wonderful. Now we're looking at this new number, n plus 2. Do we agree that it's less likely to be prime? What is the impact of n being prime? Well, we know n is not a multiple of 3. How often will we have multiples of 3 for n plus 2?
Of the time.
Why 50?
Because it either, if it's not n, then it either has to be n plus 1 or n plus 2.
Good. So 50% of the time, we know it's going to be multiple of 3. So 50% of the time, it's a multiple of 3. What about a 5? I'm sorry? So there's 4 possibilities for n mod 5. It could be 1, 2, 3, or 4. And when we add 2, it's only the 3 that becomes problems. So it's 1/4 or 25%. What if we have a multiple of 7? So it's 1/6. Is it 16.66? Like, yes. So what's a better way to view this? So if I give you prime p, what's the answer? What's the factor we need to worry about? Yeah, 1 over p minus 1. So maybe we're going to have some kind of factor in here depending on products of 1 over p minus 1. So maybe these lead to some kind of factor involving products of 1 over p minus 1. Maybe a product of 1 minus 1 over p minus 1. And that's going to be maybe the probability that it's safe. So here is maybe something we can do. And so one of my mathematical brothers, has a nice paper where he fixes the method and puts in stuff like this. And so, as much as I might want this to be a number theory class, this is not a number theory class. So I will just send you the paper. But it's worth seeing how you can try to fix stuff like this. We can come up with a heuristic. We can see, is the heuristic reasonable? And just because the heuristic fails in some places doesn't mean you should completely throw it away. It's a heuristic. It's not meant to describe everything. It might be able to describe some things, but the question is, how much can you do? How far can you push it? One of the hardest things in math is trying to figure out what do you have a chance of proving. So let's end with proof of the Riemann hypothesis. So has everybody seen the Riemann hypothesis? So there's lots of ways of proving the Riemann hypothesis. I get at least one submission a week. So I'm going to do the following. So RH means the number of primes up to x is basically the integral from 2 to x of dt over log t plus an error of size x to the 1/2 plus epsilon. I could do x to the, we have till 35, right? Okay, I could do, I think, x to the 1/2 log squared x for the error. There's a whole industry as to what's the best you can do. Among friends, you just say it's of size x to the 1/2. And then you put in an epsilon to just be very safe. If you truly need to save logarithms and powers, you can do a log squared up to x, I believe. All right, here is the proof in quotes. So xn equals 1 with probability 1 over log n and 0 with probability 1 minus 1 over log n. This is my random prime. So the Riemann hypothesis can either be done as, well, there's many ways. Two of the ways the Riemann hypothesis can be done is where are the zeros of the Riemann zeta function or the error term in the prime number theorem. So if I want, yn to equal the number of random primes less than or equal to big N, yn would be x1 plus xn. So the expected value of yn would be the sum, little n goes from 1 to big N, of the expected value of xn, right? And then that's just going to be the sum, n goes from 1 to big N of 1 over log of n. And if you want, let's not count from 1, let's start counting from 3, just so we don't have any issues with logarithms. Well, that sum is approximately the integral of dt over log of t from 3 to n. So the expected number of random primes is what the prime number says. How would we find the error? So this is the expected number of primes. How do we find the error? Well, fluctuations about the mean. What would we use? The variance, right? And so now we compute the variance. So the variance, was I calling it yn? Would equal the sum, n goes from 3 to n, of the variance of xn as we assume independent. Now, if x is a binomial random variable with parameter p, this means it's 1 with probability p, 0 with probability 1 minus p. Then the expected value of x is just 1 times p plus 0 times 1 minus p is p. The expected value of x squared is also 1 squared times p plus 0 times 1 minus p is also p. So the variance of x is the expected value of x squared minus the square of the expected value. This is the same square, as the expected value of x minus the mean squared. Has everybody seen this? And so this is just going to be p minus p squared, or p times 1 minus p. So the variance of yn is going to be the sum, n goes from 3 to n, of 1 over log of n, 1 minus log of n. No, sorry. Okay, it's p. P is 1 over log n times 1 minus 1 over log n. Okay. Can anybody quickly estimate, although it doesn't have to be too quick because we still have 5, 6 minutes. How big do you think that sum is? Do I care more about an upper bound or a lower bound? I'm sorry.
If it's how big the lower bound.
Well, I want to get a scale
Okay.
of the fluctuations.
Upper
If
bound.
I care about an upper bound. If I have an upper bound, I'm overestimating how much things are fluctuating. So can anybody give me a simple upper bound for this? Just drop the 1 minus 1 over log n. That's going to be an upper bound.
Right.
And this is approximately the logarithmic integral, the 3 to n of dt over log n, log t. But this is basically just what we were calling the expected value of yn. So the variance of yn is less than or equal to the expected value. So the standard deviation of yn is less than or equal to the square root of that. And so if the integral is about n over log n, it's the square root of n over log n. So it's basically n to the 1/2 log to the minus 1/2 n. I don't care about powers of logs. This is giving us as a heuristic that the number of primes up to n is about n over log n with fluctuations on the order of square root of n. We're basically going from the central limit theorem to the Riemann hypothesis. So you get $1 million for proving the Riemann hypothesis. For those of you who are not in person today, tough luck. So those of you who came to class, this is the benefit. Are we going to split the prize? What do you think? Any issues with this as a proof? Yeah, so why? Why is this not a proof?
Well, you don't know when you're approximating the sum of 1 over log n. You don't know if you're approximating it as a upper or lower approximation.
Those approximations I can fix. I mean, if I have a sum of 1 over log n through the integers, I can play games with that. I'm not worried about that sum. I can take upper lower bounds. I can make it precise. I can get within whatever I want. That's not a problem. Why is this not a proof?
Something about assumptions.
So where are we using independence here? So for variance, we are using the variance of a sum is the sum of the variances. So we are assuming independence. Is that legal? Well, we just had a discussion a moment ago about how if n is prime, n plus 2 is less likely to be prime. So that's one concern, that we can't really assume independence.
But that only affects the error term.
Well, but that's the whole point, is the Riemann hypothesis is the size of the error term.
Oh, that's probably.
Right. The other thing is, this is what's true for a random sequence of numbers. The primes are a specific sequence. So just because we prove a generic sequence will have about n over log n successes up to n with fluctuations on the order of square root of n, that doesn't mean the actual primes behave like this. The primes could just be very, very different. If you look at random matrices, it's possible all the non-diagonal entries are 0. Unlikely, but it's possible. This cannot be a proof. But what this tells you is a random sequence of numbers should satisfy the Riemann hypothesis. Does that make you more or less confident that the actual primes satisfy, that the primes are typical? So the primes have certain properties that a random sequence of primes don't have. You have unique factorization. You have the associated Riemann zeta function with an Euler product. So because the primes are special, maybe they have different behavior. And that's what makes it so challenging. But this is the simplest explanation I can give of why we might expect the Riemann hypothesis to be true. And again, just interchanging orders of operations, interchanging expectation and a sum. this is a good place to stop, because really, what can you do after you've done the Riemann hypothesis? I mean, really.